AlphaEarth Foundations. Google DeepMind's virtual satellite for mapping our planet in unprecedented detail. Every day, Earth observation satellites generate trillions of measurements, from optical imagery and radar scans to laser altimetry and climate simulations. But this data is fragmented across dozens of sensors with different spectral bands, spatial resolutions, and revisit schedules. High-quality ground truth labels remain scarce because field campaigns are expensive. Cloud cover, sensor failures, and swath gaps create noisy, incomplete records. And every new mapping task, whether it's crop classification or flood detection, typically requires building a custom model from scratch. AlphaEarth Foundations solves this by creating one universal representation that works across all mapping applications. AlphaEarth Foundations, developed by Google DeepMind, is an embedding field model that functions like a virtual satellite. It ingests data from multiple sources: Sentinel-2 optical imagery, Sentinel-1 SAR radar, Landsat 8 and 9, GEDI LiDAR canopy measurements, ERA5 climate data, GRACE gravity fields, and even geotagged text from Wikipedia. The model processes over 3 billion observations across 9 data sources and distills everything into a compact 64-dimensional embedding vector for every 10 meter by 10 meter pixel on Earth's surface. That's just 64 bytes per pixel, 16 times more compact than the next best learned model, yet it consistently outperforms all previous approaches across every mapping task tested. The core of AlphaEarth is the Spacetime Precision Encoder, or STP. Raw satellite observations are first processed by source-specific encoders that normalize each sensor's data into a shared latent space. The STP encoder then runs 3 parallel pathways simultaneously: a space pathway using vision transformer self-attention at 1/16th resolution to capture long-range spatial relationships, a time pathway using time-axial attention at 1/8th resolution to model temporal dynamics across the observation sequence, and a precision pathway using 3x3 convolutions at half resolution to maintain fine spatial detail. These pathways exchange information through learned Laplacian pyramid rescaling. The output passes through a von Mises-Fisher variational bottleneck that produces a 64-dimensional embedding on a unit hypersphere, conditioned on a user-specified time period. Implicit decoders then reconstruct all source measurements from this embedding, and a teacher-student training scheme ensures robustness to missing data. AlphaEarth was trained on an unprecedented diversity of data. The optical backbone comes from Sentinel-2 and Landsat 8 and 9, providing multispectral coverage at 10 to 30 meter resolution. Sentinel-1 C-band SAR and Pulsar-2 L-band SAR add all-weather radar observations that penetrate clouds and vegetation canopy. NASA's GEDI LiDAR provides 100 relative height metrics for canopy structure. ERA5 land contributes monthly climate variables like temperature and precipitation. GRACE gravity data captures terrestrial water storage anomalies. GLO30 provides global topography. And uniquely, the model also ingests NLCD land cover maps as weak supervision and geotagged Wikipedia articles aligned through eclipse-style contrastive loss. In total, the training set spans 5.1 million sites, 8.4 million video sequences, and over 3 billion individual frames, approximately 6 petabytes of data, trained for 56 hours on 512 TPU v4 devices. AlphaEarth was evaluated across 15 diverse tasks spanning land cover classification, crop mapping, tree species identification, oil palm detection, evapotranspiration estimation, and change detection. On average, AlphaEarth reduces error by approximately 24% compared to the next best method. Traditional approaches like CCDC composites and mosaics random features fall behind by over 28%. Transfer learning from ImageNet underperforms by 26%. Even purpose-built satellite foundation models like Prithvi, Clay, and SatMAE show 17 to 20% higher error rates. This consistent margin across such diverse tasks demonstrates that AlphaEarth's multi-source training and STP architecture produce genuinely superior representations. AlphaEarth embeddings are already being applied across a wide range of real-world tasks. In agriculture, simple k-nearest neighbor classifiers on the embeddings achieve state-of-the-art crop mapping across Africa, Canada, and Ethiopia, without any model retraining.
In forestry, MapBiomas uses the embeddings to monitor Amazon deforestation, while U.S. forest inventories benefit from improved tree species classification.
The Global Ecosystems Atlas project maps over 100 ecosystem types at 10-meter resolution using AlphaEarth as its backbone. For climate science, the embeddings improve evapotranspiration estimation on the OpenET benchmark and capture water storage dynamics from GRACE gravity data.
Change detection across decades becomes straightforward by comparing embedding vectors over time. Published applications include tea plantation mapping in an MDPI Agriculture 2026 paper and data center site selection by DeepMind's. The key advantage: simple classifiers on these embeddings consistently match or beat task-specific deep learning models that require far more data and compute. AlphaEarth embeddings are freely available through Google Earth Engine as the satellite embedding dataset. The dataset ID is Google Satellite Embedding V1 Annual.
Using it is straightforward. Load the image collection, filter to your year of interest, and extract the 64 embedding bands, named Embed 0 through Embed 63. You can then apply any standard classifier, a k-nearest neighbor, linear probe, or random forest, directly on these embeddings. The dataset provides 1.4 trillion embeddings per year at 10-meter global resolution, with annual layers from 2017 through 2024. Over 50 partner organizations are already using it, including the United Nations FAO, Harvard Forest, MapBiomas, the Global Ecosystems Atlas, Stanford, and Oregon State University.
AlphaEarth Foundations represents a paradigm shift in Earth observation.
Instead of building custom models for every mapping task, a single 64-dimensional embedding captures the essential information about every 10-meter pixel on Earth's surface.
Looking ahead, Google DeepMind is integrating these embeddings with Gemini large language model agents to enable natural language queries about any location on Earth. The broader Google Earth AI collection will combine AlphaEarth with flood forecasting, wildfire tracking, and methane detection models. The vision is clear: a comprehensive, continuously updated digital twin of our planet, accessible to researchers, policymakers, and organizations worldwide. Thank you for watching.
For more details, please refer to the original paper by Brown and colleagues on AR14, the Google DeepMind blog post, and the satellite embedding dataset on Google Earth Engine.
All references are listed on screen.